In this module, we're talking about acid strengths. That is, how strong is an acid, and we're going to predict this based on the structure of the acids, the molecules. So first of all, what do we mean by a strong acid? Well, the more readily a molecule releases its proton, its acidic proton, the stronger an acid it is. And this is determined by two things. This is good to know. One, how easy it is to break that bond between the proton and the rest of the molecule, which will be the conjugate base. And then, once we've made it, how stable the conjugate base is. The more stable the conjugate base is, the easier it is to make, and that means the easier it is to pull that proton off or to release that proton. So first, we're going to look at how easy it is to break the bond, and two things affect this. The first is how long that bond is. The longer a bond between the acidic proton and the atom it's attached to, the easier it is to remove that proton. So let's look at these two molecules, methanol and methane thiol. The only difference between these molecules is that the acidic proton in methanol up here is attached to an oxygen, and down here the acidic proton is attached to a sulfur atom. Now a sulfur atom, it's bigger than an oxygen atom. Hydrogen atom is the same size, so that means, that tells us, we know that the bond between the sulfur and the hydrogen is a longer bond than the bond between the oxygen and the hydrogen. And so while they both are at least a little bit acidic, methane thiol, this molecule down here, is more acidic than methanol. It's easier to pull the proton off of methane thiol than it is off methanol. And the reason is this bond is longer down here in methane thiol than it is here in methanol. The next thing that affects how easy it is to break a bond between an acidic proton and the rest of the molecule is how polar that bond is. The more polar it is, the easier it is to break. What determines the polarity of the bond? Well, at least at the first level, it's determined by the difference in electronegativity between the two atoms. Now, if that's the same, then it's determined by the rest of the molecule. Now comparing these two molecules, once more we'll look at methanol, acting as an acid, donating proton. Now here, the difference between these two molecules is that down here, in place of one of these hydrogens, we've put a fluorine. Now we know fluorine is the most electronegative element in the periodic table. And what this fluorine does out here is it pulls the electrons away from the carbon. Well, when you do that, you leave a little bit of a positive charge here, and now that positive charge attracts electrons away from this oxygen. And when you pull electrons away from this oxygen, it pulls electrons away from this bond between the oxygen and the hydrogen, making this bond here more polar than this bond here, because this hydrogen here is not nearly as electronegative as this fluorine here, so it doesn't really pull the electrons away from here. Because this bond is more polar, it's easier to break, and this molecule down here is more acidic. It's a stronger acid than methanol is up here, because of the polarity of the bond now. Next, another thing that affects how easy it is for an acid to release its acidic proton and thus be a stronger acid is how stable the conjugate base is once we make that base. The easier it is to make, the easier it is to pull that proton off. So what makes a base stable, or any molecule stable really? One really important thing is delocalization. If we can spread out that negative charge over a bigger area, that's going to be more stable than having it localized on a single atom. And the way that we can tell if a charge is delocalized is by resonance forms. Now, another thing that affects how stable a molecule can be, the conjugate base is the electronegativity of an element holding a negative charge. The more electronegative an element is in a molecule, the easier it can hold a negative charge and the more stable it is. So first, let's look at the hydrohalic acids, the hydrofluoric, hydrochloric, hydrobromic, and hydroiodic acids. In these molecules here, it ends up that the bond length is the most important factor. Now, because there's just a halogen attached to hydrogen. Hydrogen is consistent. The only thing that's different is the halogen. Iodine is larger than bromine, which is larger than chlorine, which is larger than fluorine. And so the longest, weakest bond is in hydroiodic acid, which is the strongest acid. And the weakest is between hydrogen and fluorine and hydrofluoric acid, which is the weakest acid. Now the oxoacids, these are where you're going to see resonance forms become really important. For instance, if we look at nitric acid, when we pull this acidic proton off of nitric acid, we leave the nitrate polyatomic ion, and this is one of the resonance forms. There are two others, which I'll show you in a second. But in those resonance forms, the negative charge, this one right here, is going to be spread out over the molecule. And that's a stabilizing factor. And this is how it's spread out. If we calculate formal charges on the oxygens, these two have a negative charge. Nitrogen has a positive charge. Here, 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 and here. What this tells us is that the negative charge is spread out over all of these oxygens through these three resonance forms. That's a stabilizing factor. That makes it fairly easy to form the nitrate ion from nitric acid. And nitric acid is in fact a strong acid. Now, nitrous acid, on the other hand, is not nearly as strong. And the difference is that there are only two resonance forms of the conjugate base, in this case nitrite, than there are with nitric acid, where there are three resonance forms. And this is what happens with nitrous acid when it loses a proton, become nitrite. It just has these two resonance forms. The negative charge is spread out over two oxygen atoms, not three. It's less stable, it's harder to form, and the conjugate acid is weaker than nitric acids. Now let's look at how electronegative the element is in the conjugate base. So we're going to compare perchloric acid to periodic acid. Perchloric acid, when we remove the proton from it, leaves the perchlorate polyatomic ion. Now this ion here has four equivalent resonance forms. The single bond could be here, 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 or here, which means that this negative charge is spread out over four atoms, which is true and good and stabilizing. But also, let's look at that chlorine. Now we're going to replace this chlorine with an iodine. So here, periodic acid, we also have four resonance forms. That's fine. But now that iodine is not nearly as electronegative as the chlorine. Well, it's not as electronegative as the chlorine. It's a little less electronegative, which means it can't support the negative charge as well on the polyatomic ion. And so this is a weaker acid than perchloric acid is, because of the ability of the conjugate base to support the negative charges less here than it is with perchloric acid.